morning everyone. Today we are going to see the lecture on neural networks based hybrid force position control of robotic manipulators. The outline of this lecture will be as follows. First we have the reduced order dynamic model of robotic manipulator when it is in interaction with the environment. Then we take this reduced order model represented in terms of filtered error and the nonlinear function f of x. And this nonlinear function has to be estimated by a neural network, and hence this is called neural network based force position controller. So, about that we will be seeing after the representation of the reduced order dynamic model of a robotic arm with the filtered error R and with the unknown function which has all the potential unknown parameters of a robotic arm. Then we move on to the precise neural network based position force hybrid controller of a robot manipulator, the design of that controller. Then we have the stability analysis of this proposed neural network based hybrid position force controller. Okay, so in the stability analysis we will be seeing the assumptions pertaining to the boundary or the boundedness of the system parameters. Boundedness. Okay, so boundedness of the or the assumptions pertaining to the boundedness of the system parameters we will be seeing in the end. So, this is it. Now, we will start the lecture. Now, let us write the dynamic model of a robotic system when it is in interaction with the environment given by B of q into q double dot plus C of q comma q dot into q dot plus f of q dot plus g of q plus tau d is equal to tau plus j transpose of q into rho. This is say equation number 1, which represents the dynamic model of a robotic arm when it is in interaction with the environment. Here q of t belongs to the n dimensional Euclidean space and j of q is the Jacobian matrix that is associated with the contact surface geometry, and rho is basically the contact force vector, you can say, exerted normal to the surface by the robot arm, and it is described in the coordinates relative to the surface. It is rho is a force vector which is represented as a vector of contact forces exerted normal to the surface, and it is described in the coordinate system relative to the surface. And tau d of t, as it is indicating with d subscript, so it is representing disturbances. And we have tau f that is represented by j transpose of q into rho. So, this is basically the force in joint coordinates corresponding to rho of t. So, tau f is basically given by the expression j transpose into rho, which is basically the forces in the joints of the robotic system corresponding to the reaction force that is obtained from the environment or the contact surface. Now, let us see the force constrained motion and error dynamics. Okay, aerodynamics, constrained aerodynamics pertaining to the constrained motion on a surface. Force constrained motion and aerodynamics constrained motion on a surface. Let x equal to f of q is the forward kinematic relationship that relates the movement of the robot end effector in the Cartesian space by given joint angular vector q. So, the prescribed surface can be described by the geometric holonomic constraint equation that is given by phi of x equal to 0, where phi function is defined in such a way that the Euclidean space is now reduced to the space of dimensional m from n. The n belongs to the joint coordinate q and m is getting reduced, the order is getting now reduced to m by the constraint equation. Okay, that is phi of x. Now, the constrained Jacobian matrix is given by j of q equal to dou phi of f of q by dou q, and we must note that the normal velocity is given by j of q into q dot, that is equal to 0 due to the prescribed motion of the robot arm. Now, let us see the constraint equation. The constraint equation reduces the number of degrees of freedom to n1, that is given by n minus m. So, let the motion in the plane of the surface be described by the reduced position variable. Let the motion of the robot arm, motion in the plane by the robot arm in the plane of the surface be described by the reduced position variable, that is q1 of t, that belongs to the n1 dimensional Euclidean space. Okay. Then by an implicit function, one may relate q2 to q1 by the implicit function gamma. That means that maps q2 and q1, which means they are related by the implicit function gamma, where q2 of t belongs to the space of the Euclidean space of dimension m. Okay. So, here q2 is dependent variable. One must note that now the joint variable is given by q1 of t transpose q2 of t transpose whole transpose. Okay. Now, we know where is q2 and where is q1. q2 is dependent variable on q1. That q2 q1 relationship is given by the implicit function gamma. Okay. So, now let us see that the robot constrained for motion along the surface satisfies reduced order dynamics in terms of the variable q1 of t that belongs to the n1th dimensional space of the Euclidean space. Okay, so now let us define the extended Jacobian matrix that is given by L of q1 is equal to I n1 and dou gamma by dou q1. Again I repeat, the robot is constrained to move in a planar surface, and that constrained motion reduces the dynamics of the robotic arm, and the reduced dynamic model is defined in terms of the variable q1, where q1 belongs to the n1 dimensional Euclidean space. Let us have to derive this reduced order dynamic model of the robotic system in interaction with the environment. Let us define the extended Jacobian matrix that is given by L of q1, that is given by first term I n1 and second term dou gamma with respect to dou q1, where I n1, as you can see, it is an identity matrix of size n1 cross n1. Then the relationship between the tangential velocity, which is q1 dot, to the full joint velocity q dot is given by q dot equal to L of q1 into q1 dot. So, the extended Jacobian matrix that relates the full velocity to the tangential velocity of the robotic system. Also, from q dot equal to L of q1 into q1 dot, we can have q double dot is equal to L of q1 into q1 double dot plus L dot of q1 into q1 dot. Okay. So, we can have these two expressions. Now, substituting all these expressions, substitute all the expressions into equation 1, that is the dynamic model of the robotic system in interaction with the environment. We are getting B of q1 L of q1 into q1 double dot plus C1 of q1 comma q1 dot into q1 dot plus F of q1 dot friction term plus gravity term G of q1 plus tau d disturbance term is equal to tau plus J transpose of q1 into rho. So, now this is equation say 2. Now, we can have this expression be pre-multiplied by L transpose. Before that, let us explain what is C1 of q1 comma q1 dot. We have seen so far C. Suddenly coming, it is C1, where C1 is given by CL plus BL dot. And we may use the implicit function, that is q2 equal to gamma of q1, to compute q of t in terms of q1 of t. So, that the functional dependence is shown in terms of q1 of t. Now, pre-multiply equation 2 by L transpose, we get L transpose B of q1 L of q1 double dot plus let me put that so shortly without q of q term. So, L transpose C1 Q1 dot plus L transpose F plus L transpose G plus L transpose tau D is equal to L transpose tau plus L transpose into J transpose into rho. Now, we know that J of Q1 into L of Q1 is equal to 0. This is a fact associated with the extended Jacobian matrix and the actual Jacobian matrix of the robotic system. So, we use this fact that leads to B bar Q1 double dot plus C1 bar Q1 dot plus F bar plus G bar plus tau D bar is equal to L transpose tau. Let this be equation number 3, where we used J of Q1 into L of Q1 is equal to 0. Now, this is the equation number 3 is the dynamic model of the robot motion in the prescribed planar surface with force information removed. So, here this equation we do not have the force information, that means the contact force information. Now, let us get into the filtered error concept, because we are going to derive the or design the neural network based hybrid position force controller using the filtered error based approximation approach. So, let us talk about the filtered error concept. The potential aim or the hybrid position force controllers problem is to make the robot arm to travel a prescribed constrained surface while exerting a desired normal force to the surface, and the desired motion trajectory is in terms of Q1d that belongs to the N1 Euclidean space, and the prescribed force is given by rho d of t that belongs to the space m dimensional space. The force is normal to the surface, contact surface, and Q1d represents the motion trajectory of the robot arm in the constrained surface. Okay, so now let us see, to design this hybrid position force controller, we need to follow the filtered error approximation. Let us talk about the motion error that is given by Em equal to Q1d minus Q1, where let this equation be number 4, and the filtered, let us see what is the equation, yes, number 4. Let the filtered error R is given by R equal to Em dot plus lambda Em, that is the filtered error, where gamma or lambda is a positive diagonal matrix, for the design of the controller. And let us define a force error given by rho tau equal to rho desired minus actual rho, that is given by equation number 6. So, rho of t here is the actual contact force that is in normal to the contact surface, that is defined in the coordinate system attached to the contact surface, that is your actual force vector, that is rho of t. Now, differentiating the filtered tracking error and substituting that back into equation 2, then the reduced order equation will get your reduced order dynamics in terms of or, that is filtered error, that is given by B bar R dot equal to minus C1 bar R plus L transpose f of x plus L transpose tau d minus L transpose tau. Say this is equation number 7, where the robot nonlinear function f of x is given by B of q1 L of q1 multiplied by q1 d double dot plus gamma plus lambda em dot plus C1 of q1 comma q1 dot multiplied by q1 d dot plus gamma em plus f of q1 dot plus g of q1. That is equation number 8. Okay. So, we can say that f of x is represented by this, and it is basically f function which has all the potential unknown parameters of the robot arm. Okay. Unknown parameters of robot. So, here f of x, which means x is defined as a vector that contains all the time signals to compute f of x, that is given by em transpose em dot transpose q1d transpose q1d dot transpose q1d double dot transpose whole transpose. So, this is the input to find the unknown function that contains all the unknown parameters of the robot arm. Now, we are going to represent equation 1 in terms of the filtered error and the function f of x, nonlinear function f of x, that is given by BL R dot equal to minus C1 R plus f of x plus tau d minus tau minus j transpose p, that is say equation number 9, j transpose into rho, my dear friends, it is a rho. Okay, rho is the contact force. Okay, so now this representation of the robot in interaction with the environment in terms of the filtered error R and the unknown function f of x is done to prove the force error is very small with the control scheme proposed. Okay. Now, this is done to prove force error is very small with the proposed control scheme. Okay. So, it is necessary to also work with equation 1. Okay. So, now this representation to bring the equation number 9 is made in order to make the force error much smaller by the proposed control scheme. Also, we must note that the equation number 1 also has the force vector. So, we need to work with that equation number 1 also, which contains the force information. Okay. So, which contains the force information. Okay. So, I repeat clearly, equation 9 is obtained to make the force error much smaller by the proposed control scheme. So, we also need to work with equation 1 that has a force information, that is all. Now, let us move into the neural network based hybrid force position controller for the n dimensional robotic arm. Now, let us consider a two-layered neural network that is given by this schematic. W2 transpose. So, the weights connecting the input layer to the hidden layer. Okay, this is input layer. Okay. Now, let us talk that what are the network parameters here? The network parameters are W1 transpose and W2 transpose, where W1 transpose is basically the weight vector connecting the input layer to the hidden layer, and W2 transpose is the weight vector connecting the hidden layer, which is layer 1 to the layer 2 or the output layer, and the output is represented by y1, y2 up to ym. Okay, so the layer 1 is termed as hidden layer and layer 2 is basically the output layer for our case. So, let us consider this for the neural network based position force hybrid controller. Okay. So, though where here sigma of x is basically the activation function involved here with the input x, which is nothing but x into W1 transpose. Okay, so, the output from the hidden layer is basically the activation function sigma of x and W1 transpose. Okay. Now, the neural network controller is given by tau equal to W2 hat transpose sigma of W1 hat transpose into x plus kV L of Q1 into R minus J transpose into rho desired plus Kf gain multiplied by rho tilde minus V. So, this is equation number 10, and here W1 hat, W2 hat are the current weights of the actual neural network obtained by the training algorithm of the network parameters. And having given the control equation for the neural network based controller, we can also see the neural network weight update law that is given by W2 hat dot equal to F multiplied by sigma of W1 hat transpose into X into L or whole transpose minus F into sigma hat prime W1 hat transpose into X into L or whole transpose minus kappa into F multiplied by norm of L into R multiplied by W2 hat, and then W1 hat dot is given by G into X into sigma hat prime transpose into W2 hat into L or whole transpose minus kappa, the small constant, multiplied by G into norm of L or multiplied by W1 hat. So, given the equation of the controller of the neural network based hybrid position force controller and the network weight update law is also given here in these two equations W2 hat dot and W1 hat dot. Now, let us see the design parameters. What are the design parameters for the controllers are F and G. The design parameters here in the controller are F and G, which are nothing but the positive definite matrices These are nothing but the positive definite matrices, and kappa greater than 0 is a small parameter. Okay, it is a small parameter. Now, we have to see the robustifying term in the controller, that is V, that is given by V of t equal to minus kz multiplied by the Frobenius norm of the vector z hat plus zb into R, where the vector z hat is given by w2 hat 0 0 w1 hat is the matrix which contains the overall weight estimate, okay, overall weight estimate, that is w1 hat and w2 hat collectively called the overall weight estimate of the network. That is represented by the matrix called z hat, which is called the overall weight estimate matrix. And we also have certain one more matrix that is called z tilde, that is given by w2 tilde 0 0 w1 tilde as the first and second rows respectively, is called the overall error matrix. So, there are two matrices associated with the robustifying term of the controller, that is one is z hat and z tilde along with zb, where zb is a small constant meant for the boundedness of z hat. Okay. Now, let us talk about the assumptions on the system parameters and desired trajectories. Now, let us see the assumptions on the system parameters, particularly on the boundedness of the system parameters and desired trajectories. So, first case is the desired trajectory boundedness. This is q1d dot q1d double dot of t, whose norm is less than equal to qb, where qb is a known scalar bound. Likewise, we can have the matrix Z, which is defined in such a way that it is the matrix of ideal weight vectors of a neural network whose output is exactly equal to the target. So, that Z matrix is given by W2 0 0 W1 as the first and second row, where W1 W2 are the ideal weight vectors, which are constant weight vectors of the ideal neural network, which gives the output which is equal to the exact target. Okay, so here the ideal weights are target or constants and are bounded so that Frobenius norm of the matrix Z is less than ZB. Okay, so ZB, as I mentioned earlier, is a known bound. Now, let us talk about an important topic, which is closed loop error dynamics using neural network controller. Okay, so we have stated the neural network controller. Substitute the control equation into the equation number 7, that That means substitute neural network controller into the reduced order dynamics, that is given by equation 7, we get closed loop error dynamics that is given by B bar R dot equal to minus L transpose kV into LR minus C1 bar R plus L transpose into W2 transpose sigma of W1 transpose into X minus W2 hat transpose into sigma of W1 hat transpose into X plus L transpose into tau desired tau disturbance plus epsilon plus V. Okay, say this is equation number 11. Now, expanding from equation 11, we can have the expansion of that is expanding sigma of W1 transpose X in a Taylor series about sigma of W1 hat transpose into X, and with some other manipulations we get B bar or dot equal to minus L transpose kV into LR minus C1 hat C1 bar into R plus L transpose into W2 tilde transpose into sigma hat minus sigma hat bar sigma hat prime into W1 hat transpose into X plus W2 hat transpose into sigma hat prime into W1 tilde transpose into X plus L transpose into W plus V. Here W of t is the disturbance term that is given by W of t equal to W2 tilde transpose into sigma hat prime W1 transpose X plus W2 transpose O of W1 tilde transpose into X square plus tau d plus epsilon, where O of z square denotes the terms of order 2 in Z. So, which is nothing but O of W1 tilde transpose into X power 2 denotes the terms of order 2 in W1 tilde transpose into X. So, here the neural network weight estimation error, these errors are given by W1 tilde equal to W1 minus W1 hat and W2 tilde equal to W2 minus W2 hat, where W1 is a constant and W1 hat is the estimated one obtained from the actual neural network. And also we must know that what is sigma hat is nothing but the activation function of W1 transpose into X of the input argument, and sigma hat prime is given by the derivative of the function, that is the output, that is given by the activation function. So, dou of sigma of z with respect to dou z, where z equal to the input, which is W1 hat transpose into X. Now, to bound W of t, that is the disturbance term, we can have this expression, that is W of t norm is less than equal to C naught plus C1 into norm, that is Frobenius norm of z tilde plus C2 into the Frobenius norm of z tilde multiplied by R norm with C0, C1, C2 are computable constants expressed in various bounds. Say C0 is a computable constant that is expressed in terms of various bounds, that is given by C0 equal to epsilon n estimation error plus dB disturbance bound plus small c0 into zb, where small c0 is a constant, small constant. Okay, now let us see the final topic of today's lecture, which is stability proof using a Lyapunov function stability analysis. So, let us consider the Lyapunov function stability analysis given by half R transpose B bar into R plus half trace of W2 tilde transpose into gamma inverse W2 tilde plus half trace of W1 tilde transpose G inverse W1 tilde. Okay. So, here F and G are symmetric positive definite matrices. And now, taking the time derivative of the Lyapunov function candidate, we get L dot equal to minus R transpose L transpose kV into LR plus trace of W hat transpose multiplied by gamma inverse W tilde dot plus sigma hat minus sigma hat prime W1 hat transpose into X multiplied by L or whole transpose plus trace of for the W1 matrix W1 tilde transpose into G inverse W1 tilde dot plus X into sigma hat prime transpose W2 hat into LR whole transpose plus R transpose L transpose into W plus R, sorry, W plus V, with assumptions W1 dot equal to 0 and W2 dot equal to 0, because W1, W2 are constants. Now, we get L dot given by minus R transpose L transpose kV into LR plus kappa multiplied by the norm of LR whole multiplied by trace of W2 tilde transpose into W2 minus W2 tilde plus trace of W1 tilde transpose into W1 minus W1 tilde plus R transpose L transpose multiplied by summation of W plus V. Okay. So, now using various norm in inequalities, okay, using various norm inequalities and the bounds of the disturbance term W of t, we get the boundedness of position error as LR bounded. Okay. So, LR norm greater than BR, where B suffix R is given by kappa multiplied by ZB plus C1 upon kappa whole square by 4 plus C naught divided by KV. So, which means that the position error can be made very small by increasing the gain KV, that is what it means. So, this is regarding the boundedness of the positional error. Now, let us talk about the boundedness of force error, that is rho tilde. So, now substitute the neural network controller, say given by equation number 10, into the error dynamics, that is equation number 9, we get B L R dot equal to minus C 1 R plus F plus tau D minus J transpose into rho minus W 2 hat transpose into sigma of W 1 hat transpose into X minus K V into L R plus J transpose into rho D plus K F into rho tilde plus V, which implies B L R dot equal to minus K V L R minus C into minus C 1 into R plus W 2 tilde transpose into sigma hat minus sigma hat W sigma hat prime multiplied by W 1 hat transpose into X plus W 2 hat transpose into sigma hat tilde sigma hat prime multiplied by W 1 tilde transpose into X plus J transpose into I plus K F into rho tilde, where K F is the gain associated with the positional error in the force domain, plus W into W plus V. Now, this equation can be written as J transpose into I plus K F multiplied by the force error rho tilde equal to B L R dot plus K V into L R plus C 1 into R minus W 2 tilde transpose multiplied by sigma hat minus sigma hat prime W 1 hat transpose into X minus W 2 hat transpose sigma hat prime W 1 tilde transpose into X minus W plus V is equal to B into R dot into X comma Z tilde. So, now I am equating this to this B. So, now you can say that from this equation rho tilde equal to B. Okay. So, rho tilde is going to be given by B upon J transpose into I plus K F, but before that we can have the pre multiplication of this equation 2. Okay. So, let us pre multiply the above equation by J to get J into J transpose multiplied by I plus K F into rho tilde is equal to J into B of R dot X comma Z tilde. Therefore, we can say that rho tilde equal to I plus K F whole inverse multiplied by J transpose whole inverse into J multiplied by B of R dot comma X comma Z tilde. So, what is implied here? It is saying that now with J transpose being non singular, so that the inverse can be possible, the force error can be reduced much by increasing the force tracking gain, that is Kf, and also we can say that the force error is bounded. So, with this I come to the conclusion that we have seen in today's class the dynamic model of the reduced order fashion or manner. Okay, dynamic model in the reduced order case, reduced order dynamic model of the robotic system in interaction with the environment, and we have seen the neural network based hybrid force position controller. And then we have seen the stability analysis of the system or the controller. Now, I can conclude more precisely that in this lecture we have seen the dynamic model of the robotic system while interacting with the environment. Then we come to the reduced order dynamic model of the robotic system in terms of the variable q1, where q1 belongs to the dimension n1, where n1 is given by the reduced degrees of freedom n minus m, and through the implicit function q2 equal to gamma of q1, we have the reduced order dynamic model expressed in terms of function f of x and the filtered error term or. Then we moved on to the neural network based controller of the hybrid position force approach, where we have the update law for the weight parameters associated with the two layered network being updated by the stability analysis involving Lyapunov analysis. Thank you so much.